Okay, so what I want to talk about today is a proof technique called proof by induction. And you want to use proof by induction when you're trying to prove that a statement is true for a bunch of different cases. So for example, you wouldn't use proof by induction to prove, let's say you want a statement like square root 2 is irrational. It wouldn't make sense to use proof by induction here because you're just trying to prove a statement for just the number 2. But if I wanted to prove something like this formula, like 1 plus 2 plus n is equal to n for all n when n is a natural number greater than or equal to 1, right? This we want to use proof by induction for. But first, before we even get to that, let's explain conceptually what proof by induction is. So, okay, here's what we do. It doesn't have to be, so proof by induction can apply as long as we have some lower bound, right? So for here, our base case, or our lowest bound is going to be 1, and then obviously the natural numbers go towards infinity. So this goes on and on and on to get to infinity. Okay, so how does this work? Basically, what we want to do is we want to prove that, I'm going to call this statement S. Okay, we want to prove that S true for base case. So the base being our smallest number, so for 1. And we want to establish that S is true for some arbitrary n. And then, or we actually, it's better, we assume S is true for some n, and then we use this assumption to prove that S is true for n plus 1. And then if we can use our assumption here to prove that it's true for n plus 1, then that means our assumption was correct. So these two things are both valid. And because we've proved the statement for n and n plus 1 and for the base case, what this means is that we've also covered all of these cases and all of these cases. So I think it's easier to see why these cases are true is because, okay, if it's true for n and n plus 1, you can pick a super large n, like whatever you want to do over here, like super large n, and obviously you can be true for n plus 1. So I think it's easy to see why it's going to extend accurately, infinitely towards infinity. But when I was first learning this, it wasn't immediately obvious to me why it was clear going this direction. And it's because this also works going backwards, right? So if it's true for n and n plus 1, it's also going to be true for n minus 1, n minus 2, and so on and so forth. And then it's going to stop at your base case. So you have like, it's going to be n plus 1, n plus 1, n minus 1, dot, dot, dot. And it's not going to extend infinitely backwards. It's going to extend to your base case of 1. And because we know this is, our base case is true, our inductive reasoning is valid. And so this is kind of the conceptual reasoning of why a proof by induction, or what it's even doing, why it works. It's kind of cool because you're able to cover infinitely many cases by really only doing a little bit amount of work for some arbitrary n, n plus 1, and the base case. Okay, so let's see how we can apply this to this statement up here. So here our base case is going to be n equals 1. So now we just verify this, right? So we just plug it in. So we have 1 equals 1 over 2, right? So our base case is true. And now for our inductive hypothesis, we assume that it holds for some arbitrary number. And just so I don't confuse it with the formula, I'm going to just use a different variable k. So let k be an n, k greater than 1. So k is a natural number greater than 1. And then I think we can do greater than equal. I don't think it matters here that much. But okay. So now, our inductive hypothesis is going to be that assume that the formula holds for some arbitrary k. So 1 plus 2 plus k equals k plus 1 over 2. Now, we want to use our inductive hypothesis. So use inductive hypothesis to show S is true for k plus 1. And once we do this, we're done. So that's all we have to do. That's all that's left. So let's just write out the left side of our equation, right? So we have 1 plus 2 plus, so we're going to k plus 1. So plus k plus 1. We're just writing this down. Okay. And now we know that this, by our inductive hypothesis, is equal to k plus 1 over 2. Okay. Now in the same step, actually I'll make it 2 steps. So plus k plus 1. Now we'll just make a common denominator here of 2. So this is all going to equal k plus 1 plus 2k plus 1 all over 2. Now we can factor out a k plus 1 here, and we have k plus 1 times k plus 2 over 2. We have this. And now, if we use our formula, or use our statement S, we see that this is going to be equal to, so here, n is equal to k plus 1. We have k plus 1 or this is equal to k plus 1, k plus 1 plus 1 all over 2, which is equal to k plus 1, k plus 2 over 2. So we see that these two things agree, and so this statement is true for k plus 1. And this means that we've proved an arbitrary k, we proved the base case, we proved k plus 1, that this statement is going to be true for all natural numbers greater than or equal to 1. So, yeah. And then, just another, so this is introduction and proof by induction, but another question that might come up is, can you do for other number systems, like for the integers? And at first, like let's say I wanted to prove statement T true for all Z and Z. So true for all integers. And it might seem like we can't even apply this because integers go from negative infinity to infinity. But we can do this actually if we consider 0 as our base case, and then we can do 2 proof by inductions. So 1 for all Z plus and 1 for all Z minus, treating 0 as the mutual base case between them. So yeah, we can also do it for integers. Okay, thanks. Hopefully this is interesting.